So hello, can you hear me? Please let me know if you can hear me well and see me well. So drop in plus, minus. Plus, minus, can hear, see well. We have 6 people online. It will be quite intensive day today. Need to cover quite a lot of material. Okay, good. 7 people, let's wait for others. We want you to get ready with the template that we've done so far as yesterday. I think nobody actually finished the homework from yesterday. That's why I'm forced to show some of the how to solve it a little bit more, and then then for the homework you will have another homework with 3 segment robot arm that you need to implement yourself. So for this one I will help you out. So here we left over at creating these 2 segments, and then we started calculating the error or the loss, right? The error of that part. Then we also looked at the derivative of the error function, so that we got already done quite well. So that's great. So that part is done for us. Then we have also these parts. So just a second, while people are connecting, I will start copying the equations to the new slide, and then we will solve them together quickly. So here, let's drop it in the second slide. So this will be one of the equations. Of course, then we need also this equation for changing, so the stochastic gradient descent. The simplest procedure for changing the parameters. The fun thing that theta, like this label of the angle, is the same label for the parameterization in the deep learning. So that's a great thing that we already have that connection. So then also the derivative of the loss function, the error function, so to say. So now we are missing, I guess, the next part. So now we're 9 people online, but maybe let's wait for a few minutes for more people. So. Meanwhile, I will probably start writing the equation that is still missing here. So let me share the full screen. So I also advise you to learn the LaTeX. By the way, okay, so maybe I will later share some tools for the LaTeX as well. But so okay, I don't want to distract myself. So partial, not partial, frac of, so next we need to, if we have the loss function, then we need the derivative of the that other part that is here. So r theta 1, so this function where we had there is the vector part. The vector part is something that I need to look. What was the notation for that part? P matrix. Okay, cool. P matrix. Then this is 0 and 2 and P matrix. And the frac of d theta I guess still we can do it like that, the theta 1, and we need to find out what is this output. Okay, cool. Oh, sorry, only the multiplication is actually the dot product, and you don't usually write it like that. Okay, so cool. And to get that derivative, basically what we need to do is that, of course, the multiplication part do not change, so the multiplied constants stay the same, so we don't change that. But we need to calculate derivative of the rotation matrix, so that will be frac of this one with regards to d theta 1, like that. So yeah, so we need that part. That is the derivative of the rotation matrix. And let me show you how we're gonna do it. So here we'll add this one. So and this is going to be your first task for today. You're going to need to write a code for the derivative of the rotation matrix. So you will need to submit that as a task in the Google Classroom. So basically you need this item. This item is missing right now. I will open the task just in a second. So you already have the rotation matrix. Let me show you what I mean by that. See here we have the rotation matrix, right? So, and we have it also here, the rotation. So what you need is the rotation of the rotation matrix, and then you need to implement this part. So to do this part, and then we need to calculate it here, dr1 rotation, the rotation of the theta 1. So okay, so is the task clear, and do you know how to solve it, or you don't know it at all? So is the task clear? Plus, minus. If minus, then tell me what is not clear regarding this task, and maybe I can help you out. This will be in the Google Classroom, one of the first tasks. Just a second, I will launch it. Classroom. So you can submit either your code or just that function. So that should not be that hard. So I will add the task 4.2. 4.2 implement derivative of rotation matrix, and we will need to implement just that one function. Not really difficult, hopefully. I added as a preparation material for this session, beforehand, yesterday, that you should look at derivative tables. So if you looked at the derivative tables, you should not be an issue to implement this. Why is this necessary? Funny question. So, okay, but it's good that you ask questions. It's better that you ask questions than you don't ask questions. So this is necessary because we want to do the thing that we started yesterday. So we want that our robot arm reach the target point of y, so the y without prim, and to reach the target point we use the stochastic gradient descent using the derivative with regards to theta for the loss function, and then we move step by step closer to our target. And to have this whole derivative calculated, we need to calculate in parts. So one option is that you just open, just to fill everything inside the one function and then open it with like a mathematical expressions. That is one option. The other option, a smarter option, would be just to split the task in multiple parts. So we yesterday split the first part, the loss function part. Now we need to solve the y prim part. So the y prim part is here. So if you look at here, the y prim is calculated by this equation. So to get derivative of theta, we need this equation to be solved. And here we need the derivative of the rotation matrix. So yesterday you all answered very quickly about some of the very simpler derivatives, like, and this one is again very simple one. So remember, all of you like typed immediately the answer for this one. So here we have the rotation matrix. So maybe I will drop in the also how the rotation matrix looks like, so you can have a quicker option to look at it and then derive it. So the rotation matrix looks like that. No, load it, right? So you need to derive this with regards to theta, and provide me a function for derivative of the rotation function, or rotation matrix. So rotation transformation. So is the task clear now? Plus, minus. If it's not clear, then ask question what exactly is not clear. Hopefully I answered the question why we need this, but if it's still not clear, then try to write it a little bit more detailed question. And let's wait for somebody to implement actually the derivative of the rotation matrix. So if you type in minus, then let me know exactly what is not clear. So great, I see at least one plus. So what about others? Like, I think like it's better to try to engage with our sessions. As I say, if you start like slacking on these things, later it will be harder. So we need a function that uses derived rotation matrix. Yeah. So I mean, so you need to implement it in the Python, because if you implement this in the LaTeX and copy me the LaTeX code, I also will be happy. So no problem. Just give me the answer. But if you implement it in Python, we will be able to use it immediately, you know. So because we want that robot arm to move to the direction that we would like it to move, right? So in that we will need to implement it anyway. So I'm happy that Kristaps and Armand is interacting with the chat. What about others? So do you need some help with regards to basic derivatives? So let's ask that one, this question. Do you need a help of basic derivatives plus minus? So that like the absolute, like the idea that yesterday we just derived few functions. Do you need like to help explain what to do, like step by step, or do you get it what you need to do? Okay, nice. I assume that Armand is getting what we need to do. Not so cool that other people are not interacting with the chat. So 2 people understand what to do. That's great. So I'm better. I will show something then. So okay, great. Everybody understands what need to do. So that's excellent. So let's wait for some answers coming in. Okay, I have one winner. Yes. So Betty, the person who did the greatest game before, but the person who is not interacting with the chat is submitting the code, and let's see if the code is correct. So Betty did it first. That is excellent. So the code is correct. That is great. So we have one winner already. So for Betty, I can try to advise is to try to implement the code so that this one segment that we have already, so the one segment of the maybe if you have the top chat enabled, it has delays. Just a section. Maybe you have the top chat enabled, it has delays. Not sure what you mean by top chat. If you can explain what you mean by that, I can try to understand it better. But I have the stream going on, and I see the chat, so I don't know what you mean by that. But yeah, so Betty is giving the correct answer. Let's see. So we have 3 answers coming in. That is beautiful. And you could try to implement that one robot arm already moving to I mean the one segment of the robot arm moving to the correct position. If you can do that, that would be even greater. So I see that some other people are also sending the correct answers, except there is something strange. So I think someone, oh no, this is okay, this is correct, yes. So Armand's answer correct. Then Christoph's answer, I think also correct. And Betty also was correct. So you should be able already to implement that this one segment of robot arm is already moving to the correct direction. That would be great. But let's wait. So I see that there were more people working on it. So I'm really happy actually that the answers seems like that you already feel a little bit comfortable with the Python and the math. So that is our desired goal, that you get more and more comfortable. So that's great. We have 3 answers coming in. So again, it's better to have the answers now than later, because you still will need to submit them to get the scores. But like if you do it now, then you save yourself time, you know. Okay, so what could I do? Seems like that all of you should be able to do it. Okay, if you look at the derivative tables, you could easily find the geometric derivatives, where you can see that you would have like the derivatives of cosine with regards to theta. If that is the case, then it's minus sinus and so on. So you just can look up those trigonometric tables. And if I have here dr, so what already some of you successfully did is following, minus s, c, like that. So that's great. So I will not actually drop this in the Jamboard, because this is one of the tasks. So okay, this is done. Then let's go to so we have this calculation here. So then we need to calculate with regards to the loss, all of this stuff. So just let me show you quickly the notation, so you feel comfortable about it later as well. By the way, I just realized that I did not show the answer. Okay, so what I do, I will add the answer not in the Python code, but in the just in the LaTeX code. So let me add on the slide number 3, there will be derivative. Okay, derivative we have, that is great. Then the next stuff that we need to do is try to put all of our pieces together using the chain rule. Like when you have function inside the function, you just multiply them using the chain rule. So that's not difficult at all. So there will be, we'll need to write it down. Try to make all of this stuff out with the LaTeX. Just a second. So let me share the full screen probably so it'd be more interesting. Full screen, okay. So we had to calculate with regards to the loss function. So the loss function will be here. This is going to be matcal L, the loss function, MSC. So not really MSC, but let's call it loss function. I just don't want to have the division in the that's scaling stuff. So here theta c dot this one. Then we need to multiply this by the derivative that we just calculated yesterday. So this will be minus 2 of y minus y prime, y minus y prime. So these are going to be those vectors like that. So let's see how it looks like. So d of that is cool. And then because that is a matrix form, so but all of the elements are pointing to the theta, we could just sum them together. So sum. So we want to have the scalar form, not the Jacobian. So like that. Okay, so great. So we have the answer for the d theta. So I copy this inside the slide 3. Okay, cool. And now you need to implement it. That's it. That is really not difficult now. But we will also do the two-part arm as well, because otherwise I'm worried that maybe you don't get something. So, okay, here we have the implementation of the D rotation. That, like many of you did this great. So that's cool. Then we need to implement the loss function part. So one thing I like to do is add the loss here, loss 0, so that I can track my loss to see it visually here. Let's round it by 4 numbers. Just I want to see it on the top as well, because the loss should reduce, right? So then the loss itself, so again, this is not required, so you don't need to like actually calculate the loss, but at the same time it is nice to do it just to see that your derivative is correct. If the loss is not reducing, then that would mean that your derivative is not correct. By the way, the division, like the mean square error division by n, is just a scalar, so it doesn't really matter in this case. Like in some cases, actually it matters, so it makes it easier life by the changing the step size and stuff. So that's fine. Then we also need, actually, I would allow to have the step here on top of it. So the step would be e minus 2, like that. So the step is up there as well. So those things. So the loss function we have. Now we need to use the equation that I just wrote with for the theta, d theta 1, and this one will be d theta 1 mp sum of so the dr By the way, as you see that hopefully that is something that you also need to understand for the deep learning material that we will have, that the derivatives, those formulas are constantly changing. They are depending, they actually not the formulas, but the values in the matrices for the derivatives are not fixed. They are depending on the inputs. So I have seen students thinking that they would calculate the formula and then basically it will be constant for all the iterations, but basically you calculate like a formula, this function, but the inputs are like for every layer, every function in function, everywhere they change all the time. So you just like kind of produce a computer program where you have different kind of scalar inputs. So this one, then of course the matrix multiplication. So we need to matrix multiply by this one. So this constant of the vector by length. So this one, and then we need to multiply it by the the error that we have. So for the error part, there was this. So it's actually interesting to think about it because we can use the dot product there as well. So dot product minus 2 of a target point minus, oh sorry, there should be the multiplication sign of the minus joint, like that. So now we have the theta, hopefully, and then we want to apply that with a stochastic gradient descent with minus the theta multiplied by a step, the alpha. Butiba step is the alpha, right? So, and if I run it, so hopefully if it's gonna work correctly, then I will also post the stuff to the Jamboard. So let me see, maybe there were some problems. Okay, I guess the problem is that about the last part probably, because here we have the vector. Okay, so it should work in general. Just a second, I will add the breakpoint. Just want to check, because I think I could use directly the vectors, not the pairwise multiplication. Just a second. So these guys should give us vectors. Yes, there is a vector, that is correct. So, okay, the problem is in the order, I guess, because I cannot do the dot product in that order. Okay, but if this is a vector by vector, then we can multiply a vector by vector using just the simple multiplication, or you can have the you can also have the dot product. If you add here like this, then there will be a dot product, or you can use the just multiplication for like two-dimensional vectors like that. So that should be okay. So this part is fine if I run it. Maybe also share the full screen. Let's see if it works. So the full screen. So see. So we have a poor robot guy with just one part of the arm. So the poor guy cannot reach the goal because it's not so it can reach some goals, you know, like if you point it very precisely to the point where it's at the tip of the end, right? So there it can go, but it cannot like reach all of the positions. So this is great, except I need to. I advise you to delete this last line of the input, because otherwise if you press escape it don't quit the app. So okay, I will add this part of the code to the Jamboard as well. So you can, but I will not add the rotation matrix anyways, because you did it already. Okay, that's great. So let's take a quick pause here. So post plus minus when you are ready with one arm, with one segment of arm, with single segment of arm. So then you can post plus in the chat. If you have some problems, please post some information regarding your problems. And then we'll move on to the two segment arms. When we will have the two segment arms ready, then you will have for the homework 3 segment arm, and then we will quickly move to the actually regression task, the first proper machine learning task. So you see that it's alive. So I have 4 pluses coming in. That's excellent. I would like to see more pluses coming in, some interaction with the chat of more. So let me know. So let's wait for one more plus, and then I will show you about the next part of the arm. Okay, I see the pluses coming in. That's great. That's great. So okay, let's move with the second part of the arm. So the second part of the arm. So great. I like it that it worked for you. So the second part of the arm, again, not so difficult. So you just copy these lines and use them as theta 2, right? Theta 2, R2, 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 like that. That's great. Then the tricky part, but at the same time, it's really not tricky because you did it for the computer game of the asteroids. Because in that case, you also had to calculate not to calculate, but to multiply the joints in this correct order. So to multiply joints in the correct order. So here we need to copy again the joint. So the idea is that each this segment contains of 2 joints from the copy from the previous one and then the new one. So this one is the copy, and then the new one, the new joint, is calculated. So this is calculated with the series of, so basically you can think of it as the point that is rotated, translated, it's actually translated, rotated, translated, rotated, or something like that. So basically you can play around actually with the order of things, but in general this is what you did already before. So only difference is here actually that we are not using the translation matrix, and that's why we need to plus the translation, but not to multiply it. But if you convert this code with the translation matrix without the just the translation vectors, then it would be exactly like in computer game where you have RT, RT, and stuff like that. So here we have R1. Then it is so that actually this is the same stuff from the first joint. Maybe we could even use the first joint stuff, but I'm a little bit scared because, so no, actually I could, I think, use it. Let me think. So yeah, we could use it. So the only thing is, again, pointers, right? I have in mind more tasks of pointers. So again, we need to copy the stuff. So one way to copy the contents of the array so that we don't have a pointer, we can use like this, the MP array or MP clone or whatever. So I just don't want to rewrite this line. That's why I do it. Basically, it's basically the same stuff. It's just like repeated chain together. So here, then we chain together the next part. So the next part is R2 and again multiplied by this guy. So that's great. Now we have two arms, two segments of the arms, and then we need to add it here, like that. So this one is cool. Then the theta for the next segment, okay, there we need to derive it a little bit further away. At the same time, because there is a plus there, so that is easy, because the plus eliminates our problems. Because if there would be a rotation in matrix multiplication, then this would not be considered as a constant with regards to theta 2. So in this case, it's a really simple equation. So the simpler equation is d theta here 2 to like that, and here will be, of course, so the R1, so this will be just R1, because the multiplication part stays the same. We need to access only, okay, maybe it's not actually that clear. So how could I make it a little bit clearer? Okay, so I will rewrite a little bit my code so it's readable a little bit better. So the segment, let's call it segment vector. So I can move the segment vector here. This will be one part. Then I will show you here the segment vector like that. Then there will be segment vector here. So now the code is more readable, and hopefully you can see the pattern of the derivatives there. So here there will be multiplication of the derivative of this guy plus segment. Then in the second part we have the derivative. So okay, so we need the second joint. Second joint is here, R2. And this part is the same. And then it seems like that I don't need that first part, except maybe I forgot some line somewhere, because it doesn't seem right. Okay, yeah, I forgot the line. I forgot not the line, but the bracket here. That's why I was thinking why it's different equation. So here I need the bracket before that part to translate it after the after the translation, then rotation to all of that. So that there is this one missing, and now it makes sense. So now this part of the this part for the theta 2 doesn't change. That is great. And then we would multiply the inner part. Okay, so it should be, I think, then R1. So that is a constant, it doesn't change, that's right. So, and in this case, then with the constant, so yeah, so that is cool. So the way how you can then think of it is if we calculate the constant with the first one, constant with the second one, and then ignore the first one, and then we have derivative only of the second one. And for the second one, derivative would be here the R2, dr2 multiplied by segment. Wait, not like that, but like that, segment. Okay, hopefully it's right. I think even I don't need that bracket here, but let me check. So if it will work, then I will post the code. If it will not work, then we need to debug it. It seems like it's working. Okay, let me show you how it works, and then I'll share the code. And if you have some questions, then please ask. So now let's see, can it reach the goal? So now it's kind of slowly changing the inner part of the angle. So it's a little bit more difficult problem, because now it cannot just like change one angle and get the best result. So now they kind of need to work in tandem. So the first angle is kind of, they both move, but one moves faster than the other, and then it reaches to the target point. So, and now it again will try to change the angle. So it works. That is great. So let me just double check. I think if I remove that part, it should also work. If it will work, then I will definitely, so I don't think that bracket is important. Oh, it's nice, beautiful that you say that it works for you. So now it will be like, it will slowly probably change that inner angle. It will just take forever, because the stochastic gradient descent algorithm right now is not that smart. There are better ways to optimize the functions. So okay, now we have really simple type of the code. And of course, hopefully, looking at this, you can have in mind very easily how to create the same code for a 3-segment object, right? For 3-segment robot arm. So this is not something like out of the blue, you know, like you should be able to understand how to add 3rd segment now, because I gave you so much information. So basically, that will be one of your homeworks, to add the 3-segment part robot arm. And then let's move on to the next part. By the way, let's have the question first here. Is the 2-segment robot working for you? For 3-segment arms, yes, there will be 3 dot products, and it's just like chaining together, basically. So in this case, the chaining together is a little bit maybe even easier, because now you have like just the brackets with the plus. So maybe I can rearrange. So if I rearrange this equation like this is actually, this looks exactly like the, so this is a fine transformation, transformation that is rotation times x plus t, or like translation, right? Or in deep learning, you use it like weights times x plus b bias. So basically, this part of the function is like super basic stuff, and you can chain them together and make all sorts of interesting things. So I see 3 pluses coming in. That's great. Let's wait for a few more people finishing this one. And then I have in mind some other interesting things to do. And then we'll move to the actual deep learning, not deep learning, but just the machine learning task, the first machine learning task with all of the information that you learned so far put together in one place. So I have those pluses coming in. Let's wait. Let's wait for a few more pluses. I have 3 right now. So I see a few more pluses. I added also the homework stuff, so you can basically finish your homework quickly if you just like continue what we did so far. So now let's do some other fun tasks. So let's ask a question. So depending on the information that we did the last 3 times, I remember first we got that you think that your Python knowledge is about 8 or 9 or 7, but I think there's many 8s or 9s. So my question is now, so how well you think you know Python 1 to 10? So I think yesterday there were a few people saying 6.5, like three sessions before they were saying 8, 9. So what do you think now? And then I will give you another small task and like question, and let's see how well you know it actually. Okay, 0 is also option, but then that will not be true because you already submitted really good work so far. So I think that so we're moving slowly down. I see that, you know, like 8, 9, then we're 5, 6. Now we got 5, 3 and stuff like that. So as I said yesterday, smart people know that they don't know much, you know. So the smarter you get, the less confident about your own knowledge maybe sometimes you also get. So, but still, we have at least Christop's thinking at 5. So let's see, maybe you're right. So again, let's keep with our protocol that we're not trying to be a monkeys and write the code as quickly as possible. Funny. So yeah, for those of you who are going down to the 1, then there's no place to go anymore. So sorry for that. But so okay, so don't be a monkeys and don't try to write the code as quick as possible. But then just please answer in the chat what do you think will be the outputs. So here, let me copy some stuff. So here, let's see. So we have. We have the just a very simple code here with the list and the function where we add items in a for loop. So what will be the output? What will be the output here? So please type in the numbers that's going to come in the output here. So I hope the task is clear because like it's not that difficult, right? Maybe you are already a little bit scared about my experiment so far. But okay, the Kristaps with the highest confidence so far gives his first shot. What others think? So please don't be the monkey type of coder. You know, like quickly type in and then try to beat the answer. So this is about thought experiment. Just think about how the code works and type in quickly. What do you think? So I have still the only one answer. Really? Others cannot think what will be the answer at all? At least those are you saying the 4, 5, and 3 on the Python knowledge, you should be able to answer it quicker, sorry. So please answer it quicker. So I have two answers. One is saying that he agrees with the first answer. But there were more people like saying that they have confidence on. Okay, so we have 4 answers. I think those were, except Martin, who is also a little bit confident of Python, is not answering for some reason. Maybe he's scared of my tricks. Okay, so cool. Now we have the answers coming in. We have the answers coming in. Maybe there's a little delay as well in the video. Sorry for that. So, okay, so then we'll have the next question. So you know that there exists the thing called the threading. So threads, right? So the threads are a cool thing where you can parallelize the code, right? So let's ask some question in the chat. Do you know what is the thread? Do you know what is threading or threads or threads in C++? There is a threads. There is a JavaScript threads. There are threads in C#. There are threads in like Java, in Python. Like I think in C there are a little bit different kind of threading options. But so do you know? So plus minus basically. Do you know threads? So if you type in minus, then basically that's also fine. Then I need to explain it a little bit. Maybe I even need to start looking for materials on threads. Okay, probably a little delay of video. That's fine. So okay, so almost all of you who are engaging with the chat say that they understand what is threading. So the threading is that you can parallelize your code by running the functions in multiple like CPU processes. All of them execute at the same time, right? So let's then have some changes in our code. So my changes in the code would look like this by using the Python threads. And now, please tell me, so that my question will be simpler. Can we predict now what will be in items list? Can we predict the order of the items list now? The order of numbers in list. So yes or no. Can we predict it or can we not predict it? So and if you say that we can predict it, maybe you can please then type in what will be the numbers, or if you say that you cannot predict it, then you just say no, that we cannot predict it. So still waiting for some answers. We have a lot of answers. So 1, 2, 3, 4, 5 answers. Let's see. Let's wait for Martin maybe as well. Martis, sorry. So I guess those guys who said that they know Python at 5, 4, or 3 or so, you can a little bit downgrade yourself, because we can predict it, and the answer will always be from 1, 2, 3, 4, 4, 0, 1, 2, 3, 4, and when you run it like 1,000 times, it will be the same answer. And if we increase this one to 5,000 or whatever, you will also have the same answer always. Never there will be a different kind of answer. Like it will be exactly like it would be with like just with the two functions called one by one. So why it is like that? Do you know it? Why it is like that? Plus, minus. I'm here afraid to answer. So again, the funny thing is that all of you guys who've answered no, we're like so confident about it. You like next time when I ask you questions, like be prepared that everything is counterintuitive. So why is it like that? If you have ideas, then type it in something. If you don't have any ideas, then you can type in minus. So the Kristaps, who was confident that he knows the Python at 5, types in minus. Very interesting. So, by the way, this behavior is the same in multiple languages, not only in the Python. So this behavior is something that basically threading works. So don't be. So you should not be like afraid of threads, but there is tricks with the threads. So okay, I see 1 minus, not seeing the correct answer from anyone yet. So let me then ask another question. So let's add here something interesting like print I like that. So you know there is this this Einstein, I mean not was it Einstein double slit experiment for the theory of relativity, I think, or something. So now the Armand is saying that Python, there are Python variables are atomic. That is not the correct answer. But now the funny thing is also the execution speeds are not the correct answer. So, but it's great that you're thinking with your head. So now we are observing our I. So now the question is, can we predict order of items now? Yes, no. So when we add this line 8 with the print, can we predict the items now? Now I'm trying to observe my items. Would it change the behavior or not change the behavior? What do you think? Maybe somebody looking at this code and my question can now answer my previous question. So I guess Emils is saying no, cannot predict the order. Armand is saying again the no as in the first question, and Kristaps is now not so confident, no idea now. What about others? So, well, I think it's quite fun in general, like just to see like this regression of a regression of this kind of confidence on Python. But at the same time, I think you also appreciate that when we do these small experiments, you get smarter, and then you can then you can write the code in a way that you don't fool yourself. So I see just 3 answers, probably everybody else super scared to answer now. So now if I run the code, so you see that the order is unpredictable now. The order is not the predictable order that was before. So why is that? So to answer that, there is a 3-letter combination that explains everything. And this is the same actually not only for the Python, but for other languages like JavaScript as well. So first thread finished with second thread call. No, sorry, that is not the answer. So now the threading kind of works. If we just add the print and start observing our items, like in double slit experiment of the like Einstein experiments, then it starts working. But actually, there's nothing related to that. So the three-letter name that it is fault at this is a global interpreter lock. So in Python and in JavaScript and in like many interpreter type of languages, I think like Lua and others, you have like the situation that the interpreter part, so that is real-time kind of compiling but not really compiling, kind of needs to know everything that's happening in the code. That's why you cannot run any thread at the same time. Even if you have like 100 CPUs, it will never run at the same time. So the only way how it can run at the same time is if you do some IOU procedures, input-output procedures. So these could be either writing a file, for example, sending data to some kind of socket on the cloud, or for example, waiting asleep, or writing on the console something. So anything regarding the input-output while it's waiting for the disk to read, that moment it can run something else in other thread. So that's the way how this works. And the only way how to bypass this in the Python is to use the, I think, yeah, this is the only way. So the multiprocessing. So the multiprocessing is like threads in C++, like threads in C++, but they are about 10x complicated than threading. So if you read about how you can then pass the variables to the childs, and then there are like crazy examples that maybe I can share you later, where you can screw everything up by thinking that it works in one way, but the memory allocation works in a completely different way. Basically, this is something you need to keep in mind if you work with JavaScript, with Python, and with all sorts of weak languages. So Python, problem, JavaScript, this is also the problem. This is actually never like real threading. Python, JavaScript, maybe some other languages as well. So that is one of the reasons why I really hate like all of these Electron type of apps that are built with the JavaScript. Like one thing, like it's really easy to make them like fast iterations, but they are like lagging and not nice, or like UX and stuff, like the responsiveness, because all of this is running on one thread. Like it's really hard to make a proper JavaScript app in multiple threads. It's like even more harder than multiprocessing on Python. So, okay, that was a small thing on the side. Be prepared for downgrading your Python knowledge in the next sessions. At the same time, actually, it's not downgrading, it's actually upgrading. You just like reduce your confidence, but you increase your knowledge. So that is good trade-off. So let's move on to the next task. So the next task will be first proper regression task. So regression in machine learning. So this will be your first proper machine learning task. And I will try to lay it out in a very simple terms. And if it's not clear at some point, please let me know, because it's quite important that you understand just the basic notions why this is important and how this is actually constructed. So let me just quickly, I just want to quickly find my notes, in a sense that I don't want to write the numbers just from out of the blue. I just want to use some numbers that I already used in some other examples. So here will be the regression is specific task for trying to find scalar value. So we will try to find the scalar value of the price of the house. So try to predict. We will try to predict. Try to predict scalar value of house price of house depending on the some of the some features of the house, depending on features of house. So that's going to be our task. So you can imagine, you can also try to predict stock prices, right? Depending on the features of the stock prices. That also could work in some fantasy world. So because the stock prices are zero-sum game. So here we have the different kind of houses. I'm trying to just illustrate what we're trying to do here. So if you can notice that these houses differ mainly on the number of stories, so how big they are. Of course, there are also some other properties for the houses. You can say like what year has it been built, like what neighborhood this house is, like, and how close is the, let's say, scrapyard or school. Maybe all of these parameters, the features can determine the price of the house. Oh, nice. The Armand is saying that he got the three-segment robot arm working. So you can then submit the homework, and you already submitted it, and you then get 1,000 points. And if you get 1,000 points, then this is really good way to earn high grade in this course. So that is great. So I'm happy for Armand, who is submitted a three-part arm. So then let's see here. So there will be some of the properties, features. So let's start by the most basic feature. So we will make a code for the most basic feature, and then later we will make a proper learning with a lot of features for the house. So let's say the basic feature will be the floors. So floors or the stories. So floors, we have one floor here. We have two floors here. We have three floors here. And we have 5 floors, if I counted correctly in that picture, in this one. And then let's imagine that the price is something that we multiply by 100k. Price will be, let's say here, so this will be 0.5, let's say 0.2, no, okay, that's going to be too cheap, 0.7 times 100k euro. I don't know, like, don't take this like too serious. I mean, like, this will be just an example. So here this one will be then a 1.5. Then this one is gonna be 4.5, and the last one is gonna be at 9.5, for example. So now we need to predict this outcome, and of course we need to make our model so that if we add more features and train new model, we can still predict the prices. So it should not be like a total idiotic simple model where you like use like I don't know, like Excel linear separation or something. So we should try to make it kind of with the potential of being smarter, just using very simple terms just to illustrate it. So the way how we formulate it formalize it in the equations usually is using some kind of like vectors or sets or things like that. So here, let's say the first input set of the x's will be, so there's one. Let me quickly give you the formalization of this. Okay, what is missing here? This one. Okay, and then the other part will be 7, 0.7. Just a second, I will drop in some lines of the LaTeX code so that it would look nicer and be formalized. The problem would be formalized. So copy this one and drop in here. So we will use, actually in deep learning and machine learning in general, like you usually use these kind of notations where you have the x as your input features and the y as your target output. So in this case, this is how it looks like. So I will actually probably create a small note in my own notebook so that I don't lose all of these numbers. Just a second. Notes, text. That's fine. Okay, so and let's then start constructing our model. And for the constructing of the model, so let's go then to the flat. Okay, but before starting constructing the model, is the problem understandable? So is the problem definition understandable? Plus minus. By the way, you can see the very big, very high similarity between this task and the robot arm before, because again you have like some kind of predefined inputs, and you have some desired outputs, and then you will have some theta or whatever parameters in between, right? So do you understand the problem definition, plus minus? Let me know, please. So I see one plus coming in. If it's not clear what we need to do, then type in the question. You can also type in some comments, but basically you should already feel the direction where we will go now, because we already did all of the linear algebra, we did the calculus, and now we are at the point of partial derivatives and the actual machine learning task. So I see only one plus yet. Okay, seeing more information coming in. Okay, that's interesting that we got also minus, but it would be great if you a little bit explain what is not clear. Are we trying to find a correlation between the variables? Predicts y from new inputs, right? That is correct. Means is saying correct direction that we will have in a, so actually that is not bad, bad question. So when we will have the model, so what will happen? So we will have some kind of y prime that we will get from our model, and if we give the model some kind of the x of some unknown variable, let's say there will be so it's 1, 2. We are missing actually the four floors, right? So if you give some kind of like variable x that contains 4 floors, right, we will predict what is the price for that house. Or if we give 6 floors, we again will try to predict the price. So that is the correct direction of the thought. So great for that you asked that question. Like if Armand is giving us minus, it'd be great to see some question in regards to that, but let's go forward and hopefully the minus will turn to the plus. So we need to find that M stuff, right? The model. So we want to learn the model. So the model, let's try to then to write it down somehow. Let me think what would be the easiest way to start coding this. Not the coding, but writing the equations. Okay, so the model stuff. So we will predict stuff. So let's write down. So we want to predict the y prime price using some kind of model that will be parameterized. So with regards to x, something like this, for example. But the model itself, we can immediately start writing what it could be. So one way to write is using the affine linear transformation. So this would be just a linear model. So C dot, the dot product, or in this case, if we have just one dimension, then just simple multiplication plus B, right? So this will be our, like this could be the one of the most basic models, but actually this is not properly written right now. So a little bit better would be to write, let's call this an H model. So H with an input of X, Y, and B, like that. So now the prediction can be calculated using, let's say, this kind of small linear model. In this case, the linear model, the learnable parameters would be the weight matrix and the bias here. Before, in our robot arm, there was theta, the only parameter that we changed. Now we want to change two of them together at the one function. That's why it's a partial derivative, because we need to then calculate derivative of multiple parameters within the same function at the same time. So, but this is not yet everything. I think it would be great, nicer if we somehow try to make it a little bit smarter. So we could make it a little bit smarter, this model, by applying some extra functions. Let me think. So first of all, the output is always from some defined range. So the output is from, let's say, around from 0 till 10, or maybe let's say if the output would be till 20 or something. So okay, sorry, this is interesting, I pressed the wrong button. Okay, so we could use maybe a sigmoid around it. I will show you in a second the sigmoid as well. So here we could use the sigmoid function around this one, like this, for example, and then we can multiply it by some constant, C dot, and this constant, in this case, let's say this will be 20, so because we want to somehow scale it a little bit. So now the model is a little bit more interesting, but of course this is still far away from proper like deep learning models, but still this is a good start for us now. So again, I need to close this because I'm always opening it. So this will be our model here. I will quickly show you the sigmoid as well. So I will copy this one so I don't lose it. And the sigmoid function. The sigmoid function is also a function. So it's 1 over, so let me write it down. So sigmoid will not have parameters inside that function. So let's use some kind of arbitrary input variable here as, let's say, a. and this will be then the frac over 1 divided by 1 plus, then this will be the exponent of the minus a, like that. So this is our function, so that we will apply over that linear transformation. So let me quickly copy this. By the way, while I'm typing all of these equations, and they are just the very beginning now, so if you have some questions, then type in the chat so I can stop and explain some stuff. So this is the other part of the equation. Okay, and now let's try to quickly, okay, maybe I will again need to copy it because otherwise I lose it. Okay, so let's quickly implement this stuff. Just, I mean, not everything. I will just implement, so you don't need to write actually the stuff that I write now, but you can if you want. So import matplotlib pyplot as plt. I just want to display for you the sigmoid function so you can look at it a little bit, how it looks like. So again, we'll start with an, okay, let's call it a as it was in our equation, np lin space from -10 to 10 with, let's say, 100 points, and then we want to calculate it using the function. So let's call the function also here def sigmoid of, actually I actually advise you to implement this code as well, because we will need it in a second. So 1 divided by 1 plus np of exponent of minus a, right? And here we would then calculate plot of a comma sigmoid of a and plot show. So now we have this code here, and if I run it, I get very nice sigmoid here. So if I add the sigmoid here, so one thing that you can notice is that it's from 0 to 1, and if I multiply it by 20, then we have a scale from 0 to 20, and that means that we will not prognose or predict any values that are like in minus, because the house prices cannot be in minus, right? That is one thing that we can kind of help out ourselves. So we have this equation so far. Let's then ask the next question. Okay, but before asking the question, so let me kind of illustrate some of the things more of this stuff, maybe just trying to make sure that you get it. So I will color with red those parts that we will learn. So initially, when we start when we will start our code, we will initialize the weight matrix and the bias matrix as or not only that there will not be matrix in our case, there will be just scalars, but as zeros, for example. They will not be defined in the beginning, but we will learn them. So these will learn. So these will be the learnable variables, and the x value is something that we will use as data inputs, right? And then if we pass all of this information through our function graph that we have here, so our function graph is really simple one right now, very small one. If we pass like x through our small function graph, we get the y prim. That is our predicted value. So my question is, the first one is it clear so far? Plus, minus. So we want to learn those weight and bias in order to predict the house price from the input. And my question is now, is it clear so far or not clear so far? And if it's not clear so far with regards to our small model, the model is the small function graph, then maybe try to write exactly what is not clear. So we are trying to build a small mathematical function that will predict the house price depending on the floors. And the floors is the x, and the price that we predict is y prime. And to learn the weight and bias, the w and b, we'll have to fit it to existing dataset, and our existing dataset is in the previous slide, those 4 items. So if Armand is posting a minus, it'd be great if he could elaborate on that, but so we can move on to the next part. So the next part is what kind of error function could we use, or the loss function, to evaluate how good is our model, So what do you think? Knowing what we already did with the last 3 sessions, so what kind of loss function could we use to evaluate how good is y prime here? So let me quickly find my stuff here. I can start writing it. So we know the y, right? So the y, that is the correct house price depending on the x. Okay, so thank you for Armand's elaborating a little bit. The math will become a little bit more and more in this discourse, but so yeah, you should kind of just probably try to work with it more, and you'll feel comfortable with it more. It's great that it get the general idea, so that's what I wanted to have right now. So the mean square error, that is nice, so that is not bad idea. Again, so we can use, actually we even don't need to rewrite it. I can just kind of try to look it up. Where was it? We can use it from the robot arm, the mean square error, that is correct. Where was it? And even I don't need to change that much the outputs here. So in this case, the I could be all of our samples, because we could look at all of our samples together in one kind of batch. So basically, we will not look at each sample separately, but we can look at all of our samples as a vector, right? That's and calculate the mean square error for all our samples at one go. So, but just to simplify our stuff, maybe we can just drop out those i's. So, because otherwise I need to always write the i's, and I don't want to write the i's. So, like that. So, basically, the idea is that we will look at all of the samples together. So that's quite important, because we don't want our gradient to be jumping in every direction. So this is one thing. So now, if we need to learn the weight and bias, what is the next thing what we need to do? From the robot arm example, you already know that. So what do we need? Do we need to to calculate our weight and bias? So these are our learnable parameters. So on this question, maybe there are multiple parts, but you can try answering what do you think? A and X and A we need. So it's always fun to see the stuff. So the way actually it's really great that you interact with chat. That makes me understand what you understand and what not. So here you're saying A and X. So the X is actually X is something that we know already because that is in our data set. So of course we need that, but at the same time we know already that. So the A is really fun to see that you think that we need A, because A is actually the same thing that we have up there. So the A is the inner part of that function, W times X plus B. So if I latex it here, you see that A is this part. So up here, if I kind of write it, mark it somehow, so this thing is A. The output of that equation is the A. So we don't need actually A. So we know it completely already. So, but what do we need? So do you have any other ideas? Any other ideas? So I mean, what are the next steps? What should be the next steps to learn weight and bias? By the way, this example is really simple. Like very similar to the robot arm. I think that this is very natural step-by-step experience where you start by linear algebra, then robot arm, and now you get to the actual problem with the housing prices. So if you think about what you did in the robot arm to learn the theta angles, so the weight and bias is basically like theta angles. So Kristaps, I like the Kristaps is engaging with the chat, but the y prim is, again, it's not what we need, because y prim we already can calculate if we have everything that we need. So of course at the end we need y prim. So my question then is a little bit clearer. So what should be the next steps to learn the weight and bias? So what do you think? What would be the next step? What should be the next step? By the way, you should be able to answer it because you already know all of this stuff. Plus minus as well. If you don't know the plus minus, we need initial guess of weight bias. Okay, that's interesting. That's really, I really like how you're engaging with the chat. Initial guess, which can be correct in the future. It seems like you think kind of in like a programmer or something. Like it says, if you think more in like a mathematical way, I'm like inviting you to think about the robot arm example. So we just did the robot arm. How we did it? So what should be the next step? So we don't want to guess the weight and bias. We don't want to be walking in the darkness and stumbling all around. We want to use the beautiful math. So what should be the next step? How we can learn the weight and bias? Using math. Any ideas so far? So please think about the previous like robot arm, and if you have no ideas, like you don't know ideas how to learn the weight and bias, then just print in minus sign. That's really sad, but at the same time, it's great that you're honest. Hopefully, when we will end up with this, then you will feel confident about this, because before, if we go just few slides before. So we go a few slides before, we have exactly the same problem formulation for the robot arm, right? So now, if you look, the theta is kind of like the weight matrix, and we have all sorts of constructions around the weight matrix, right? The rotation matrix, and then the multiplication, and then addition of the next arm, and then again rotation, and then we have the loss function, and then we calculated derivatives. So the derivatives is the way how we can make sure that by changing the theta or the weights using the stochastic gradient descent, we get what exactly? So let me, while I'm typing this, maybe you can answer in the chat. So what will happen to loss when we will apply SGD, stochastic gradient descent, to weight and bias? So let me try to write it down for you here in this slide now. Where is my equation stuff? So again, so we would have y prime then. The y would be then minus alpha some step, or it's called the learning rate, and then we would multiply this step by c dot by the frac of the L mat call of the, my question by the way is in the chat, so mat call MSC of the x for y and y prime, and this we would have with regards to the, or basically in this case we partial weight like this. So if we apply stochastic gradient descent to this using this equation, what will happen to the loss of mean square error? So what do you think? What will happen with the loss? So knowing what you know so far. By the way, again, plus minus. I mean, like either give me the answer or just type in minus if you don't understand it still. So this is what we want to do. By the way, I will kind of copy this equation again to my notebook so I don't lose it. So this is again quite simple question. Please, could you answer it? Like, if we apply this to weight, what will happen with loss? By the way, if you implement the robot arm and look at the loss output, like if you calculate the loss, then hopefully you should answer that. And also remember the parabolic function last time, and where we were like jumping in the parabolic function. So the loss will be smaller at every iteration. I like that you have some ideas in the chat going on, but the weight and bias. So let me start trying to write down. So weight and bias at the beginning will be zeros. Then after the learning iteration, it will be something different, and this something different will produce lower loss value. So if you remember, yeah, last time, so I will try to quickly find the image from last time that all of you answered correctly, that I asked you multiple times, like what will happen in the next step of the jump in the loss function of the mean square error, what is parabolic function, right? And you all got it right. So you all understood that the loss would be reduced every time when we apply the stochastic gradient descent function. So if you remember from last time this picture, hopefully it comes to your mind now. Remember that we moved the error closer to the zero, and then we started oscillating around zero. So we would get lower loss value. And also the same thing applies for the B, so the bias. So these are only two learnable parameters here. We don't have any other learnable parameters here. So if we apply that one like this, so I will get it, PNG, so like that. So then with this partial derivative, so the partial derivative is almost no different from simple derivative. So here, if we apply both of them together, or even if we apply one of them, but most likely like it will not work, it will actually not work well. So if you apply both of them together, but actually if you just apply one, it will also try to kind of go to the zero, but it will be unsuccessful probably, but maybe, I don't know. So anyways, the idea is that you apply both of them, and each iteration when you apply them, you get closer to the zero loss value, right? Do you understand it so far? Do you understand the model so far? Model and training so far, plus minus. If minus, then please type in exactly what is not understandable. By the way, the derivative of this then all of this like a large function that you know, like you enter within the next function. So this is just like a mathematical step-by-step operation that we already did with the robot arm. So this is again, you should do it here. But it's great that I see finally two pluses. So hopefully we are starting coming out from the confusion. So we are coming out from the confusion into the understanding of the machine learning, hopefully. So we have two pluses. And I saw actually one like for the video appearing right now. So seems like that somebody got happy understanding what machine learning is. That is great. So we see two pluses. What about others? I just want to make sure that we are all on the same page. Please let me know. Are you understanding it? If not, then please tell what you don't understand right now. And then we'll move quickly to implement some part of it, and for the home I will give you some other part of it. But in general, like I guess like you will try to do this at home, but at the same time I will try to split the task in at least in two parts, so that those of you who are struggling can still get a decent number of the score for the homework. Okay, the Armands is still giving minus, but he said at some point, I think, that that the general idea he understood. But really, I don't know, like, what else, like, if you point in minus, then you should be really specific now about what is not clear. But okay, so we got really not so high response right now, right? But let's go to the code now and try to somehow make it maybe a little bit clearer. So let's do a little bit of coding and then come back to the homework and the basic tasks. So here we have the sigmoid stuff happening. So the sigmoid, we can actually delete all of this stuff, because this is nothing actually related to the beautiful graphs. It's related to the mathematical stuff regards to model for predicting prices. So the predicting of prices is much more interesting than drawing the graphs. So here, because with the predicting prices, if you can predict the price of the house, then of course you can do all sorts of cool things like manipulate the markets and stuff. So here, let's see, we have these two. I just copied the stuff from the slides, right? So MP array, so we have two of these vectors of values that we want to as an inputs and outputs, right? So this is one thing. Then we also have, let's say, what we need also weight. So this will be 0, bias will be 0. We have sigmoid already. Then we need the linear function, def linear. So the linear function will contain as an input the weight, bias, and x. So the linear function is something that we will return. So let me think about it a little bit. I think we could just so if this is just a scalar value here, so this is just a one scalar value, so we don't need actually proper dot products here, so we can use just a multiplication. So x, if the weight matrix would not be scalar value, but let's say 2 by 2 matrix, that is also possible. So there is no like restriction. It can be a matrix as well, and actually in deep learning it's always a matrix. So then it will be dot product. So now we have the linear function here, right? Then we also we have everything, I think, for prediction of the value. So we can call this as a def model, and the input of the model is actually the same thing as a linear function, like that. And the output would be then, the return would be a sigmoid of the linear with all of these parameters, weight, bias, x, multiplied by 20, the scalar that we defined, right? So this is our model. And then let's see, we can also have the y prim. We can predict immediately from all of our x's with one call model of the weight, bias, and all of the x's. So one is that we can have a for loop and go one by one, but we want actually to learn and calculate it by batch. If I'll use like batch, then that means that we can have average of our gradient at the same time. So we can calculate average, so we don't need to do the for loop. We could do the for loop, there's no problem, but it would not be efficient. So we just write down here the y prim and have or maybe just run it. Let's see what we get. So now we get something that is not very valuable. We get prediction for every house that it is worth about the 1 million, and so 10 by 100k. And but that's what we need. That is reality, because we have not yet learned the weight and bias. So we need to learn weight and bias. So then the next step is that we need to calculate the loss function, right? So def loss, and for the loss we have the input of y and y prim. But basically the y prime actually we could define it. If it would be mathematically correct, then you should actually write here all of this stuff here, because the y prime is not really the initial value. It is like calculated value. But we can use y prime because that would be make simpler, because otherwise the equations would be so long. I just don't want to make them too long. So that's why we should use the y prime here. And also the loss function is something that we use only for the training. And when we train the model, then we can drop the loss function in the bin, like in the recycle bin, garbage, and then use only the model with the trained weights and biases in the production for estimating the prices of the markets or whatever. So here we have the return of the y minus y prime. If I remember that our formula was like that, let me check what was the formula that I wrote in the y prime squared. So the order here is also kind of important, because the derivative will be different if you change the order, of course. So this one is the like that. Then what we need is, so all of the derivatives we need, so to train it basically. So just to write down the operations, what you need to do next is, so there will be, let's say, 4 epoch. So actually it's called epoch when we train all of our data set in range of, let's say, 100, or let's say 10, or whatever, like maybe 100 is too much, let's say 30. So we'll go through our epochs, and we will then, let's say, we can actually write it down here. We'll predict our prices, and then we can also calculate our loss. So this will be y prime. Let's write it down properly. Y prime, and the loss. The loss will be calculated using the real values. So, oh, I forgot actually to have the mean part here. MP mean, like that, right? So then we calculate the loss of y prime. So we calculate our loss value here. And before that, we need also to train the weight and bias. And so to train the weight and bias, we will have the alpha. The alpha will be the learning rate. So the alpha learning rate will be 1e minus, basically we can use the same as in our robot arm, e minus 2. And here, then we need to calculate the derivative of y with regards to loss function, with regards to loss. So we need to calculate this to do, and apply this one to the weight matrix. Oh man, what happened here? So weight matrix. To apply, it means that just the same way as we did in robot arm, with regards to the loss, and this we will multiply by learning rate, the alpha, and the same also for the bias, dB, the bias, and also this is something that we need to do. And to calculate all of these things, I would highly suggest that you calculate it step by step using these kind of derivatives of each of these functions, like d with regards to the dv with regards to the linear function here. So this one, think you should be enough with what you have here. So return something to do. Then I'll also calculate with regards to the b, here. And then also the sigmoid, of course, you need to calculate with regards to the a, because there's no other input parameter here. By the way, you can also calculate the derivative of so that you could calculate derivative of with regards to the x here. That could be very useful later, because if you chain together multiple linear layers, then it would be proper, like basically proper neural network with the hidden layers. And the idea is that you don't want to change the x if this is your input variable. So it doesn't make sense if you change the number of floors, right? But it makes sense if the linear layer is inside your model, like deeper, like in the deeper layers. So where the x is actually not the x, but this could be also some kind of hidden state value. So you have this thing as well. So you need that function, and then so this is d to d or derivative of a. So then you need again the derivative of with regards to the model, of the weight. So model. Okay, model we can also write down like that. So you need to do this. You need to do also the derivative with regards to the b. And finally, then you need to do the derivatives with regards to the weight and bias d, v, return, and the b, return. Right. And then you just, by the way, here you also would need more stuff, I think, probably, because, okay, weight prim, right, yeah, you definitely would need more stuff here, probably like that. Maybe you would not need some of that, but anyways, so it'd be like easier to write it like this. So then at the end, you would use these functions to calculate the outputs of those derivatives. So here we need actually the inputs, so the y prime is all we need. So that means that we will move this one here like that. And actually the loss we also could move here, and here we would use the y, and here will be the y prime, right, and there will be the x. And now we need also derivative to bias with regards to the loss. So let me just type in what I mean by this is derivative with regards to loss function, and the same for all other functions. So you go step by step backwards to calculate the derivatives, and then apply those derivatives to the weight and bias. And this is actually these operations of stepping back the loss, the error, is called the back propagation. So that is something that you use all the time in the deep learning. Like even in the state-of-the-art models, you use the same idea. So this is going to be your homework. You need to implement these derivatives and make sure that your loss reduces, and you can learn to predict these values. And we will try to help out for those of you struggling next week. And next week we will start doing more advanced models. So if there are some problems of catching up with all of these things, then yeah, let me know. Maybe write an email, and yeah, I hope that it's actually quite fun in the sense that you kind of start understanding why I mentioned that everything is with regards to the mathematics and how these deep learning models work. And you can start imagining what we could do in the future, like how powerful mathematical models we can build. So yeah, please try to struggle through these tasks. Don't make them for the don't leave them for the future, because they will get more and more difficult, and at the end you need to somehow gather the score for your mark for the course.